All right, guys, we're going to move into our discussion of inverse trig functions, okay? This section 9.5, all right? So uh, we're going to recall the graph of the sine of x, right? Now, there's no good reason why there should be an inverse of the sine of x, because as you can see, recalling one of the conditions for inverses is that the function be 1 to 1. So clearly, a horizontal line thrown through the sine graph will intersect it infinitely many times. So therefore, justifiably, it should not have an inverse. But uh, but we need the inverse of the trig functions. Your right triangle trigonometry would have shown you that, okay, and required the need of it. So what we're going to do is we're just going to take a chunk of the sine graph, okay, the smallest chunk over which it's 1 to 1. That smallest chunk is going to run from this negative pi over 2 value to pi over 2. So here it is. We've isolated out that chunk of the sine graph right here. And clearly that's 1 to 1. And clearly then it will have an inverse, which is a function. Now, of course, if we take its inverse, um, then we flip it across the y equals x line. And if we flip it across the y equals x line, we've changed a number of things, okay? So yeah, I know it doesn't look a whole lot different, but the curvature is significantly different, okay? This portion of the sine graph up here is what we call concave down, okay? Concave down. This portion is concave upward. So, and they, of course, they switch at the origin. The inverse would have the opposite flow. The right side of the origin would be concave up. The left side would be concave down. Okay. Now, let's consider going back here. All right, that we've isolated the chunk of the sine graph between the x values of negative pi over 2 and pi over 2, and then the y values between 1 and negative 1. So therefore, when we take its inverse, as we know, in the inverse, go back there, on the inverse, the domain of the function becomes the range of the inverse, okay? So again, we were only interested in that chunk from negative pi over 2 to pi over 2 of the sine function. So that designation now becomes the range of the inverse function, okay? And of course, our sine function normally only flows with the y values between negative 1 and 1. So then that becomes our domain values over here. So this is our inverse. As we know, we cannot isolate the y out of x here with any kind of analytical methodology. So we come up with a new name, much as we did with logarithms. We just refer to this as the inverse. Y equals the inverse sine of x. Older textbooks have used the notation arc sine for inverse to avoid the confusion of this implying to the negative first power, which it does not. So in its context, we would understand this to be the inverse. So as it goes then, for the inverse sine, we're taking a chunk of the sine graph between negative pi over 2 and pi over 2, that smallest interval over which it is 1 to 1, okay? We're flipping it across to y equals x, okay? And we're going to call this a very short-lived function, okay? Operating with a domain simply between negative 1 and 1 and a range between negative pi over 2 and pi over 2. Yeah, okay, so now we're back. We're looked at just the inverse sine. Now let's go and look at the inverse cosine, okay? So likewise, there is much the need for the inverse cosine, although likewise, for all intents and purposes, the argument would be there is no inverse because the cosine is not 1 to 1. But unlike the sine, on the interval from negative pi over 2 to pi over 2, the function is not 1 to 1. You can clearly see right here between these 2 points, it's not 1 to 1. So that would not be the best interval, the best chunk of the cosine graph to take to develop its inverse. Rather, we're going to say from 0 to pi. From 0 to pi, the cosine is 1 to 1, and therefore that would be the interval we'd be interested in building its inverse. So here's the chunk of the cosine graph with the x values between 0 and pi, and of course the y values between 1 and -1. Now, of course, for inverse conditions, we're going to flip that across the y-axis, flip that across the y equals x-axis, and of course, flipping that across the y equals x-axis, let's think about where the points are going to go. Okay, so this point is pi comma -1, so that's going to move to -1 comma pi, which is going to be up here, and this point, which is 0, 1, is going to move to 1, 0. So the inverse cosine is going to look much like this, okay? And again, it's going to live with the domain values restricted to -1 to 1, and the range values running from 0 to pi, okay? So we have set up the conditions over which we define the inverse sine and the inverse cosine, okay? Both with a domain restricted to -1 to 1, but with a range a little bit different, okay? So the range for the inverse cosine is from 0 to pi. The range for the inverse sine is from -pi/2 to pi/2, okay? However, the domain is both the same, okay? Now let's go to tangent, okay? Now with the tangent function, all right, the tangent function, we know on the interval from -pi/2 to pi/2 is the whole wavelength, is one whole wavelength of the tangent function, okay? And of course the tangent is in one wavelength is 1 to 1, so that portion there would set up the conditions for our inverse, okay? So the inverse tangent, we don't have to restrict it to a portion of a wavelength. We can just take a whole wavelength between its two asymptotes, -pi/2 and pi/2. But of course, the range runs from -infinity to infinity. So the inverse tangent, we would find that the inverse tangent, notated here, y is the inverse tan or the arctan of x, lives with a domain, okay, from negative to positive infinity, yet the range is from -pi/2 to pi/2. So the graph is going to look like this, okay? So in other words, we can take the inverse tan of any value because it's defined for a domain that is defined everywhere. The range, however, is going to be upper bound by an asymptote at positive pi/2 and lower bound by an asymptote of -pi/2. That's our inverse tan, okay? Now we'll talk about, I'll move into another video where we talk about these operations with the inverse trig functions, okay? Right now we just wanted to get to an understanding of the graphs, okay? So in summary again, let's take a look at summary again. So for the inverse sine, we're going to restrict our x values to between -1 and 1, and our y values flow from -pi/2 to pi/2, okay? So there's a very restricted domain and a very restricted range on the inverse sine. Likewise, the inverse cosine has a very restricted domain, the same as the sine, between -1 and 1, but the range is between 0 and pi, okay, between 0 and pi, and that's our graph of the inverse cosine. And the inverse tangent, since the tangent is 1 to 1 over one whole cycle, we can define its inverse built over that one cycle, okay? And in doing so, we come up with this as our graph, which, okay, unlike the sine and cosine, is unrestricted in its domain, and is restricted by asymptotes in its range, -pi/2 on the lower side and pi/2 on the upper side. Okay, as I said, we'll get to operations in the next video.